And okay, start. So last time we start discussion about bandpass low pass transformation, and we discussed the algorithm, what you should do when you want to calculate signal in low pass range. Yeah? And the procedure was very simple. You take your original signal, you go to frequency domain, and then cut all negative frequencies. You cut all negative frequencies, and the remaining part you shift to the in direction towards zero regarding the frequency respect to which you perform transformation. And after, you have to perform additional normalization to be sure that energy of signal before and after transformation is the same. And after all the steps, you get signal, and the signal so-called in the low pass range. And we get spectrum of this signal. And afterwards, you can convert this signal in time domain and get this time domain signal in low pass range. Made also another example with more difficult signal or spectrum of signal, where you had to calculate Fourier transform explicitly. And sometimes it also happens when you don't have, when it's not known, don't have a transformation function. So we did, and we get result. And in the end, we discussed we discussed signal of C function, right, represented by C function, and we also performed reverse transformation from low pass range to band pass range. And yeah, that's how it works. Today we're going to continue this discussion, and we solve following task. So I think it's task number 2.4. And if you have any questions, yeah, just interrupt my discussion, and then we can look question. Okay, everything fine? Everything's clear? Let's get started. So it's task number 2.4, and we consider the following problem. So we have amplitude modulated signal, U1 of t equals to U0 times cosine of 2 pi fs t times sine 2 pi fc t. And we assume that fs is signal frequency and fc is carrier frequency. And carrier frequency is much larger than signal frequency. We have the following signal. U1 of t equals to, then we have times cosine pi f st, our signal part, and we have sine pi fc, our carrier frequency. We assume that carrier frequency much larger than signal frequency. So, and we pass the signal through bandpass filter, this given transfer function. For bandpass filter, we have transfer function that is given by the following expression. We have rectangular function in frequency domain, f plus fc plus capital B over 2 over capital B. As you can see, capital B is width or bandwidth of our filter. Rectangular function, f minus fc minus capital B over 2 divided by capital B. And capital B equals to 2 times fs. And now we try to do the following, we try to solve the following problems. First, we need to determine signal U2 of t, and the corresponding spectrum at the bandpass filter output. We have to pass our signal, find how the output signal will look. So let's try to, first of all, try to understand how can we do this to find output signal. Yeah. Asking also if you think us via WebEx and you know what should we do, can also. Yeah, probably it will be the option go to frequency because we already have transfer function in, and it's rectangular pulse. It's rectangular shape. Then, as far as you have for product cosine and sine, probably in frequency domain you have just combination of delta pulses, and it will be very understand what you after we pass our signal through this bandpass filter. Okay, good idea. Let's try to do this, and then we convert our signal from time domain to frequency domain. So, and how can we do this? We have cosine times sine, so we have product of two functions, and when we go to frequency domain, product goes to convolution, converts to convolution. So instead of product, we have convolution of two Fourier transforms for cosine and sine separately. Let's try to write it. We have u0, I open bracket braces, and I write what we have. We have delta pulse. First of all, I write Fourier transform for cosine, and for cosine you have sum of two delta pulses with positive magnitudes. 1/2 delta f minus fs plus 1/2 delta pulse f plus fs. Okay, this is our Fourier transform for cosine. And then for sine, we have similar expression. We have 1/2j times delta pulse f minus fc minus 1/2j delta f plus fc. It's our result. No, it's our just it start. But then we write what will be the result. And when you calculate convolution between two delta pulses, you simply combine arguments. Very simple to calculate convolution for delta pulses. Then we multiply magnitudes in front of delta pulses, 1/4j, and then I write what we get. Take delta pulse f minus fs and delta pulse f minus fc. So the resulting delta pulse will be f minus fs minus fc. Then we go to next one, and then I just need to write all delta pulses, resulting delta pulses. So if I consider second delta pulse from first braces, have delta pulse f plus fs minus fc, and so on and so forth. So have plus minus, sorry, minus 1/4j delta pulse f minus fs s fc, and final delta pulse s 1/4 delta pulse f plus fs plus fc. That's what we have. Okay. Oh. Now we can plot resulting spectrum. say we have this is our U1 of f, axis frequency. And now we try to do any information. Yeah, I forget to mention that capital B full. FS. Ah, no, I did it. I did it. And we need this information for our filter, but okay. So let's try to place all delta pulses that we have. Let's say that we have 10 cells. We have 4 carrier frequency, FC, and also minus 10 FC. So then let's say we have 3 cells for FS. S will be, let's say, FS, FC. But we don't have delta pulse with carrier frequency FS. We have delta pulse, for example, minus FS minus FC. It will be FC plus FS. Delta pulse. Magnitude 1/4J. The next one is Fs minus Fc. It will be Fs. But yeah, it's written Fs minus Fc, but of course we can rewrite it as minus Fc minus Fs. Then of course it will be easier to understand where we must move our delta pulse. Right here, Fs, Fc, sorry, minus Fs. We have 2 delta pulses. And also we have remaining 2 delta pulses with negative magnitudes. So, oh, this is plus. So one is at frequency, right, argument as minus, F minus, and in parentheses minus Fc, and plus Fs. And next one will be minus Fc minus Fs. So you can write it like this. And then it's very easy to place them on the graph. Minus Fc plus Fs will be. They go down. And also minus Fc minus Fs will be 0. And we have magnitude minus 1/4J for both. Okay, fine. Now let's try to understand how we should denote our transfer function for our passband filter. So we have rectangular. Yes. No, this is for case when FC much larger than Fs. This case when FC much larger. Yeah, this is our current assumption that it's much larger. No. It doesn't go to 0. This is typical assumption about F carrier greater than F signal. And I actually, we, I would say it's not critical for this exam. Just need to be and sure Because you have two options. You can assume that f carrier is smaller than f signal for some reason. Then plot will be different, slightly different, because you will place delta pulse on different negative range. But to be clear, we just make this assumption, like avoid any ambiguity. But in the end, actually, it's not very important to have this assumption. But we don't use this assumption to simplify our solution and to make something equal. Sometimes we do this, but not for this task. This is just to avoid ambiguities. Okay, so we have a set of 4 delta pulses. And now let's try to analyze our transfer function. So we have rectangular pulse, which placed, we have 2 rectangular pulses. One of them placed, I think we can start with second one, because it's placed at frequency. What's the frequency for second delta pulse, for rectangular pulse? We have minus, then we have carrier frequency plus beta over 2. And at the same time, beta or capital B equals to 2fs. So we can rewrite it as minus fc plus fs. So this is center frequency for our middle of our rectangular pulse. So position of rectangular pulse will be at this point. Okay, good. And what's the width of this rectangular pulse? Capital B. And capital B is 2fs. Have to go to the right for fs and to the left also for fs. Let's try to deal. Must get rectangular pulse that looks like we have this is our rectangular, not pulse, but the shape of our passband region or positive frequency range. Okay, now let's go back to first rectangular function, and then we can write argument as minus f here minus fs. I just replaced b over 2 as fs. Then we have formation where we have to place second rectangular function. So it will be there. And now you see that after pass our signal through this filter, what will remain? After our, what we have is the output of this filter. Okay, so yeah, sorry, yeah, it's also positive. Yeah, it's also positive, but nonetheless, yeah, what we have after we pass our signal. We have 4 delta pulses, have this passband. What we have output. Yes, it will be product, but what will be the result? No. Rectangular shape function is transfer function of our filter. And we filter our delta pulses. So delta pulse is our signal. So we put it at the input and the output. Same, yeah. If delta pulse matches passband passing region, then we get exactly the same delta pulse. If it's outside this passing region, then we get 0. And here we see that we pass 4 delta pulses. We have 4 delta pulses, and only 2 of them match our passing region. As a result, at the output, we have 2 out of 4 delta pulses. So I can know that delta pulse at frequency minus fs minus fc and delta pulse at frequency f C plus Fs will remain after we put through this filter our input signal. And we can simply write that our output signal in frequency domain of F, we can write as U0 over, just take magnitudes, times, and we start with right delta pulse. Delta pulse F minus Fc minus Fs, first delta pulse, and second delta pulse with negative magnitude over 4 times delta pulse F plus Fc plus Fs. This is the remaining signal after this passband filter. Okay, great. Can we do anything? We can just maybe rewrite this expression as slightly modified. We write U0 over 4j times delta pulse, and then we can write it as F minus, and in parentheses, C plus Fs minus over 4g delta, and again in parentheses, F plus Fc, no, not plus, minus. Write it as F minus, and then in parentheses, minus Fc minus Fs. So, and let's check what we need to find. So determine the signal U2 of t at the corresponding spectrum at the passband filter output. So now we have our spectrum of output signal, and what we need to find now, we need to find how the signal will look like in time domain. Now we need to find time domain signal. How we do this? We perform inverse Fourier transform. Form Fourier transform of this signal, and what it will be. So you can see that we have a difference of 2 delta pulses, and also we have imaginary number here. You can remember that this kind of spectrum corresponds to sine wave. Even if you don't remember this, you can do the following. You should know that if you have only one delta pulse and you perform inverse Fourier transform of delta pulse, domain, what? Just one delta pulse at arbitrary frequency, and then you perform inverse Fourier one delta pulse. It will be complex exponential frequency. Complex exponential. If you have cosine and sine components together, one but both. Yeah, if you have delta pulse frequency Fc after inverse, get exponential signal j 2 pi Fc, what you get. And now instead of each delta pulse, we just substitute Fourier transform. Let's try to analyze what happens then. So place a box around this expression. Our hint. Okay, now let's try to write our expression. So we place this imaginary amplitude in front of it, and then we place our exponential function. Or I can write in way as we did it before, j pi, and then we have what's the frequency? Frequency Fsc plus Fs times t minus, and for second delta pulse we have another exponential function, time domain. Or not for u0 for j times exponential function j 2 pi. Instead of writing minus Fc minus Fs, I will place minus in front of all argument Fc plus Fs times t. This is a very fundamental concept. If you have delta pulse, Fourier transform of this delta pulse will be exponential function. I would recommend you to memorize this part. And then look, we already discussed this expression, or we already discussed this situation, that if you have a function or expression exponential j alpha minus exponential minus j alpha, what will be the result? Alpha minus plus,
J sin alpha.
what will be the result? Alpha. Correct. Have 2j sin alpha. So you see that we use all the same hints every time. Sin alpha. And we just use this trick and substitute our exponential function above using this trick. And what we get? We get that we have a sine function. Get that it equals to over 4j times 2j times sine of what? 2 pi fc plus fs. Yeah, this is what we get. And just canceling imaginary first, we get u0 times sine pi fc plus s argument. So, and you see that actually you had a very short way how to get this result, because as I told you before, you have one delta pulse with positive amplitude, j in denominator, and you have another delta pulse with negative magnitude, also j in denominator. Just looking to this table of Fourier transforms, okay, it's here. This one. You see that we have this 1 over 2 the pulse minus 1 over 2 in us corresponds to this sign. But we have shown this explicit, and you just can see how it works. Okay, but it's not the end. Now we need to find the next part. It's how our signal time domain after filtering. Now we go to question B, part B. Yes, any questions? Sorry, I don't hear because of machine outside. Let it pass our. Can speak louder. You don't need to assume any amplitude because it's given. It's written that it's like it's rectangular pulse. It means that you have 1 times rectangular pulse. So it's 1. No, for delta pulse, you have amplitude of delta pulse equals to infinity. But what you have, at magnitude of delta pulse equals to 1. And when we write number near pulse, when we write number near delta pulse, we're talking about magnitude. But amplitude cannot. And for this reason, we specify delta pulses with these arrows, because they just go to infinity. And what's the meaning of magnitude? How we find magnitude? Or what's the meaning of magnitude? It's infinity. Delta pulse is infinity. Magnitude. Area, yes. Area, it means you have delta pulse, and notion of area very easy to talking about pulses. Like if you take rectangular pulse, it's very easy to calculate area, or of this delta pulse, and it equals amplitude times duration. And for delta pulse, you have amplitude equals to infinity, but duration of delta pulse going towards to zero. It's very, very narrow. But amplitude goes to infinity. But the product of these two quantities, or area of these quantities, equals to 1. Don't specify anything else. So by default, or like say that magnitude equals to 1. So is nothing else as integral of delta pulse like integral from minus infinity of delta pulse, say in frequency domain, f equals to 1. It's area. This is magnitude. We distinguish these two quantities, magnitude and amplitude, because amplitude infinite. Okay, yes, more questions?
Sir,
1 second,
Hello.
we have a question in audience. And then I
Yeah.
answer a question from WebEx.
Sir, I have a basic question.
We have a question from Leonardo da Vinci room. Then I come to WebEx. Just 1 moment. Yeah, the question that we have a negative range for transfer function of our filter. We have transfer function with positive sign, but we pass signal with negative sign, with delta pulse with negative magnitude. It's absolutely fine, because it's minus is just you can assume it as phase of your signal. This phase equals to pi. Then it doesn't cannot by simple linear filters. You cannot distinguish signals by phase. How you distinguish them? You distinguish them by frequency. Then you just check if the signal and passband range of your match each other, and you decide to the at the output or not. And in our case, this sign of our signal just tells you what happens with the output signal. For some reason, you would have a filter which will convert phase means just transfer function. Then after you apply negative pulse with negative function, you'll get positive delta pulse. It's like yes, minus times plus, it will be. That means that had question from WebEx. Yes, please.
Sir, in the diagram, you need to show
Or it was
magnitude U naught.
much louder before.
Sir, in the diagram, you need to the
What
top
did you
of a
change? Because
rectangular
before I could hear you very well.
effective magnitude.
Question. Or it's better maybe if you write in the chat, because something happened with your microphone. At the first time when you asked your question, I could hear you very good, but now something happened. I don't hear you anymore. Just write in the chat, because something doesn't work. Okay, let's go further and go to part B. Now we need to describe the input signal in the equivalent low pass range. The transform takes place with respect to frequency, carrier frequency. Now we need to specify equations in time and frequency domain, and also we need to draw signal in frequency domain. So what actually I'm going to do, I'm going to copy our spectrum that we plotted previously. I just show all the same steps for bandpass low-pass transformation. But I don't need to show you. We just need to have our signal. So we have signal, and maybe you can help me what signal to that low-pass range. Have signal. This is signal in bandpass range. Question: we need to find low-pass representation for this spectrum. By which frequency? So yeah, let's do it step by step. As you said, we have to remove negative frequencies. So I just all negative frequencies. And then I have to check respect which frequency we have to perform transform, and it's FC or FS? FC, yeah, carrier frequency. And then we also, let me just write this spectrum again, or the intermediate spectrum. And we can call it as U1 plus and F plus FC, because you move it by FC. And then you will have two delta pulses. With magnitudes 1 over 4J, 1 over 4J. And now we have to normalize our spectrum. Yeah? And while we normalize, we multiply our amplitude by square root of 2. Magnitude, sorry. And as a result, we get that we have, let's say we have square root of 2 over 4J. And we have also for another delta pulse, we have square root of 2J. So it's our E1, L, F, our signal, low pass range, filter. We can write how it can write expression for this spectrum. 1 comma L of F. We have 1 delta pulse over. I think I also forget. I forget it. Yeah, exactly. I forget to write U0 everywhere. I have to place U0 H delta pulse. Careful because it's very scalar. It's fine. Now we can write how our spectrum in low pass range will look. We have divided by 4J times U0 times delta pulse. And here, in original spectrum, error frequency was, or frequency of delta pulse was Fc plus Fs. Then we subtracted Fc. What left? Fs. And for another delta pulse, minus Fs. S minus Fs. So for right delta pulse, I'm going to write delta pulse F minus Fs. And for left delta pulse, plus square root of 2 over 4G times U0 times delta pulse F plus Fs. This is our signal in low pass range. And again, you can, now we need to find signal in time domain. And you can calculate Fourier transform for each delta pulse separately. But we don't do it. We just write directly what will be the result, because you see that you have two delta pulses with positive magnitudes. What's the Fourier transform of this? Inverse Fourier transform of this? Cosine function. Cosine function. I'm going to write this transform U1, L. Okay? And but be careful, because for cosine function, you get two delta pulses with magnitudes 1 over 2. So we have to split this scalar in front of delta pulse and rewrite it as square root of 2 over 2 j times 1 over 2. And this 1 over 2 goes to delta pulse, right? And we don't have it anymore. And what will we have left? After this transformation, yet that we have signal with amplitude square root of 2 over 2, okay, times cosine 2 pi Fs t. This is our signal in, yeah, and I forget U0. As usually, I forget U0. Square root of 2 over 2j times U0 times cosine pi Fst. So, check what we need to find. Describe signal in low pass range. Done. Find the equation. Okay. And draw spectrum. So we have everything. Draw the impulse response GL of t and the transfer function GL of f in the equivalent low pass range. Okay. Now we come to discussion about filter itself. So everything what we did before was about signals. But now we come to discussion about filter. Originally, we have filter given as transfer function in bandpass range. Now we need to understand how to convert transfer function in equivalent low pass range. What we should do, get this transfer function. And actually, we can get it, the procedure is even easier than for signal itself. So let's first plot this transfer function that we have. Just need to repeat again these two rectangular ones. Okay. Have so okay, and we have rectangular positive frequencies, another rectangular function at negative frequencies. We have zeros side. Okay, this is our transfer function. Can also specify that we have carrier frequency and minus carrier frequency in the middle, and bandwidth to capital B or 2Fs. And amplitude of this transfer function equals to 1. Okay, and this is our G of F, transfer function of our filter, frequency domain. When you calculate equivalent transfer function in low pass range, you do the same steps. You remove negative frequencies, you shift by corresponding frequency, and that's all. Don't do normalization. Don't need normalization because you don't have notion of energy. Just need to have the same amplitude. Question about phonic energy you solve while you consider signal itself. Let's do equals to 4. We remove negative frequencies. And then we shift our positive part.
Hello?
Oh, okay, now it's better. Are there any questions?
Yeah, Professor, why are we not doing normalization? Can you repeat?
Why we want to formulate what?
Normalization, why we are not doing it
Why we
for
don't
this?
normalize?
Yeah, for this part.
Otherwise, you will have because otherwise you will normalize signal 2 times. Yeah, because just the idea is the following, that if you pass your signal through the filter, you will have 1 energy. But if you go to low pass range and if you will normalize transfer function, then you will have 2 normalizations. You will have normalization for signal itself, and then you will have normalization for filter. And as a result, energy is smaller than it should be. And for this reason, we say that don't do normalization for filter. Do normalization only for signal.
Thank you, Professor.
Probably, yeah. Yes, you're right, because according to our task, okay, sorry, it's not conceptual problem, but you're right, that it should be FC plus FS. Yes, yeah, I forget. But I mean, it's not, we don't consider signal at the same time. But thank you for noticing this. So let's just write what we get after all steps. I just resulting transfer function. No, it makes sense because as I remember, let me check, because here, yes, 1 second. Just otherwise we get different result. We perform transform with respect to frequency FC. And as you mentioned, that we have middle at FC plus FS. As a result, we don't get such nice pulse centered at origin, but we get pulse at right side, like this. Our spectrum, we can call it as G plus F plus FC, or we can call it as GL of F. So this, and have the same amplitude. It goes from 0 to Fs, our frequency domain. And what else? That's all. So this is our corresponding transfer function. But yeah, I mean, it's not conceptual because just depending on numbers, you will have different results. If you would perform transformation with respect to frequency FC plus Fs, then you would get centered at origin triangular pulse. But here we have triangular pulse centered at FC plus Fs, and we perform transformation with respect to frequency Fc, our transfer function. And then we need to draw impulse response GL of t and transfer function GL of f. But yeah, we have transfer function in low pass range. But in order to find impulse response in time domain, we have to just write expression for transfer function in low pass range. So how can we describe this function? Have any 5 minds? What's the shape of this function? Fine. I think it's something. Yeah, no. Before time domain, we have to find the representation in frequency domain. Frequency domain is rectangular pulse, rectangular shape function. So 1 second, let me write rectangular function, but then what will be in the brackets? So first of all, probably it's frequency domain. Yeah, it's F. Minus, and then middle of this rectangular at frequency Fs. We write minus Fs, divide, and we divide by width. Not Fs, 2Fs. 2Fs. So now we have expression for transfer function in low pass range for our filter. And now you can calculate corresponding time domain or delay domain impulse response. Because it's transfer function. For filters, normalize signal, because we care about energy of signal in time domain, or sorry, in band pass range and low pass range must be the same. But we don't have this condition for transfer function. So we just form this shift and we keep it as it is at all. We don't not normalize. So now we just perform inverse Fourier transform, and we get this small GL of t. And if you don't remember, as I do, you can just check that rectangular pulse, but we have rectangular shape in frequency domain. When we go to time domain, we get the following. So we get that we have 2Fs times C function of pi Fs t. And in addition, we have a shift in frequency domain. If you have shift in frequency domain, you multiply by corresponding exponential function in time. Times, and then we have exponential function j 2 pi Fs times t. Fs is our signal in time domain, and C function in time domain. Now we have to
Sir,
plot this.
why is this 2 pi coming?
I think someone asking question,
Sir,
but I don't hear you,
pi-
unfortunately. Your microphone is very soft, and I barely can distinguish what you try to
sir,
ask.
I'm asking why within this psi function, why is this 2 pi coming? It should be pi into 2 Fs into t.
Two
Sir, within the psi
pi, yes.
within the psi function, it should be
Don't need this,
within the psi function. It
this
should be
sine function. Yes, we don't need this two.
yeah. Now it is correct. Now it is correct.
It was typo. Yeah.
Yeah.
We have, of course, we have pi, then 2Fs, and then t. Okay. Yeah. Now it should be fine. And
Sir,
now
I hope my voice is
another type.
audible. Voice is audible.
Oh, for some reason. Could you please type your question in the chat? Yeah, because I don't hear what you're asking about. Okay, now we need to plot this pulse response. Let's try to plot it. And we do it in 2 steps or in 3 steps. First, I will plot the C function itself. And first, we must understand at which points we have zeros, at which points our C function equals to 0. It's very easy to memorize. At positions when psi function equals to pi, have 0. What's the first point where have argument equals to pi? 1 over 2 fs. 1 over 2f. We can just, we have 1 over 2 fs, then we have 1 over fs, and so on and so forth. We need just show approximately our function. Our C function, C pi 2fs in time domain. Next, I'm going to show exponential function. And exponential function, of course, we can rewrite as cosine pi fs t plus sine pi fs t. Okay, and the question, we can start with, but let's draw first, and then we come to the question. See something. So let's start with maybe cosine function. So at 0, we have 1. Then at time, say 1 over 2, 1 over fs minus 1 over 2. So substitute, if we substitute t equals to 1 over 2 fs, here that cosine equals to what? Equals to pi. Cosine at pi will be value of cosine at pi. Calculate cosine of pi.
Minus 1. Minus 1.
So we have 1 at 1 over 2 fs, we get minus 1. And you can just show that we just continue this minus, and we have plus, and so on and so forth. So we have minus 1. No, sorry. And then we have at 1 over fs, we have 1. So this is our cosine function. Cosine function. Okay, good. Then let's go to sine function. I can write that it's cosine pi fs t. Okay, sine function. At 0, sine function equals to 0. And then if I calculate at point 1 over fs, 1 over 2 fs, what I get? I will get sine of pi. And what's the value of sine at pi? 0. We get another 0. So at on this grid, we have values equals to 0. And I can just show that in between we have positive half, then we have negative half. And I have write that it's j times sine 2 pi f s t. Okay, we have cosine and we have sine. Now we have to multiply these two parts. We have to multiply our c function and exponential function. So, and we do it for real part and for imaginary part separately. So if we multiply a c function with cosine function, what do we get? Or what's the interesting points we have? We have the following interesting points that show it lines that when cosine equals to 0, we have something non-zero. But when c function equals to 0, cosine has its maximum magnitude. Magnitude equals to 1, yeah? But with negative sign, amplitude will be minus 1, of course. And then when we multiply these two functions, we can say that at 0 we have something maximum value. Then at 1 over 4 fs, when cosine equals to 0, we get that we have 0. And then when at 1 over 2 fs, when cosine equals to minus 1, we have to multiply by 0. Again, we get 0. And now we just need to approximately show how function will look like in between. You multiply smooth functions, and as a result, product also must be smooth. And here, what you get that approximately shows the result. You have positive value times until 1 over 4s, you have positive cosine. Then you have positive range of sine times negative range for cosine. You have this line. And you just continue, then you have negative cosine with negative psi, and you get some positive range. And you can just show that it will be this oscillating. Real part will look like this. You can only specify what will be the maximum amplitude. It will be equal to 2fs at 0, and that's all. Now we'll go to imaginary part. So for imaginary part, you multiply psi function with sine, and sine equals to 0 at origin. As a result, product will be equal also to 0. Then at 1 over 4 fs, 1 over 4 fs, sine as amplitude equals to 1. Then you multiply with some positive amplitude corresponds to psi function. You will have something like this. And then you just need to take care about sign of your resulting signal. You have in the range from 1 over 4 fs to 1 over 2 fs, you have positive sign with positive psi function. So it will be decreasing, but it will be positive. Then in the range from 1 over 2 fs to 1 over fs, no, from 1 over 2 fs to 3 over 4 fs, you have negative psi function, but sine function also negative. As a result, this product will give you positive value. Have positive. And has to be careful. So we have, actually, we see that this negative half of sine matches this negative part of sine. So we can just show that this product will give us something positive. And then actually we can just continue that it will be oscillating and decreasing like this. And if we look to negative part, we see that we have something similar, but with opposite sign. It will be oscillating and decreasing like this. Yeah? Okay, it's not easy to show, but I have a MATLAB script to demonstrate how it will look like. I hope for those who are listening us online can also see the script, and you see how this function looks like. So we have this is our psi function. It's our psi function. Then we have cosine and sine. And this is how product will look like. Yeah, we have blue line for real part, and we have imaginary part for a red curve for imaginary part. Okay, and I think there were questions. Part C are shifting the figure with respect to FC. Yes, we discussed that center of passband range at Fs plus Fc, and we perform shift with respect to frequency Fc, with respect to carrier frequency. This is the reason we have this shifted slightly right transfer function in the low pass range. Okay, so but you see that we get the same result as we supposed to get MATLAB. Okay, any questions? And I think that not the end. And the last part that we have to solve, we have to find signal, output signal in the corresponding low pass range. Go to part D. Determine the output signal, and spectrum is in low pass range, equivalent low pass range, because we already have signal in band pass range. Okay, and now we need to find L of 2 of L of T. And how can we find it? We just take a result from, I think it was the first part, this one. I will copy the whole spectrum. I place it, and I remove everything what we don't have after we apply filter. Don't have this delta pulse, don't have pulse anymore, and we have only 2 delta pulses. And now we calculate signal in low pass range. Again, we get the frequencies. And we perform shift with respect to frequency Fc. And then we have to normalize our result. We have frequency. We have U1 plus F plus Fc. And we have only one delta pulse at the frequency Fs, and with magnitude 1 over 4j u0. And now we have to normalize it. We have to multiply, because it's signal. It's not transfer function, it's signal. And what we do, normalize signal when we perform a low-pass transformation. Multiply by square root of 2. And after this step, we get our in low-pass range. Square root of 2 over 4j times u0 at frequency Fs. our U. It's not U1, it's output signal. U, comma L of F. Okay. Fine. And now we can write it and write expression for the signal. U to L of F equals to square root of 2 over 4j times delta pulse, of course, times U0, times delta pulse F minus Fs. F minus Fs. And the final step, calculate signal in time domain by applying inverse Fourier transform. So L of T. Then we get that we have square root of 2 over 4j and instead of delta pulse, we place exponential function. Exponential function y f s times t. This is the final result for our signal after filter in the corresponding low pass range. Okay, any questions? Okay, let's go back in part B. This one. And if we forget to apply the same, no, we didn't forget because we have only one delta pulse. Why I did it like this? Because I can write in other way around. If you have cosine 2 pi, let's say fct, just any arbitrary frequency, and if you perform Fourier transform, you get that you have two delta pulses with magnitudes 1 over 2. Get that it equals to Fourier transform equals to 1 over 2 delta pulse f minus fc plus 1 over 2 delta pulse f plus, I don't have place, fc. Yeah, this is the reason, because you have this 1/2 in front of each delta pulse. And then we just reshaped our expression to match this form, yeah, because you need to have 1/2 in front of each delta pulse to get one cosine function. Yeah, and then we just combine one part 1/2 with first delta pulse, we multiply. We have also the same 1/2 second delta pulse. For this reason we placed outside. Yeah, because of this form or Fourier transform of cosine function. Question. And yeah, if you have other questions, please let me know. Oh. Everything clear? Now we can, if everything is fine, then we can go further and we discuss next question. So next task that we're going to discuss today will be 0.5. Still have 20 minutes, at least we can start this task. Then we continue maybe next week. Don't have enough time. Let's get started. So we have task number 2.5. And for this task, we have the following questions. Let's try to answer the questions before we start next part. Yes, it's called baseband. Calls this baseband or low pass range. Okay. Okay, let's go back. Yeah, sometimes I also confused by this definition because you have band pass, baseband, and low pass. Then it's very, very easy to lost yourself. But okay, let's go back to task number 2.5. And we see there that we have first signal xt equals to x0 times c function, and y of t equals to y0 times c squared function. We have two signals. And we need to draw Fourier transform, or we simply need to find spectrums for these two signals and plot them. First part. Then we want to perform idea is the following, that we have signal in a low pass range. And then we want to perform transformation of this signal to band pass range. Yeah? After this transformation, we try to understand what happens. And in the end, we perform backward operation. So first, you have low pass signal, you carrier frequency, analyze, we do some analysis of this result, and then we move back. We perform band pass, low pass transformation. And we try to analyze what kind of receiver and transmitter you need to have, all these steps. But let's start with the first part. We have two signals in time domain, and we want to find spectrums for both signals. xt equals to x0 times psi function by t over capital T. And if we perform Fourier transform of this signal, to make it easier, we can say that we can write it as x0 times psi function phi t times capital F, where capital F equals to 1 over t. And then after this Fourier transform, we can write it as x0 times, you have F in front of psi function. Calculate Fourier transform using our table. I can rewrite it as x0 times 1 over F times capital F, like this. Now you can just Fourier transform from our set of transforms. Where is this set? Here. So you have psi function, but instead of capital T, you have F. And yeah, instead of F, small f, you have T. Now you can just rewrite it as rectangular shape function in frequency domain, rectangular shape function, and we specify that we have in frequency domain, don't have any shift. And what's the duration of this rectangular pulse? What's the duration of rectangular shape function in frequency domain? Yes, it's f, but then we have to replace it because we don't have f in our original problem, but we have 1 over t. And as a result, we get that our signal in frequency domain can write it as x0 times capital T times rectangular pulse, rectangular shape function, f times capital T. So this is our Fourier transform. Okay, fine. And before we go to next part, maybe we plot this signal. this spectrum. So we have this is our x of f. We have infrequency, and we have rectangular, and it goes from minus minus 1 over 2t to 1 over t, yeah. And then we have amplitude x0 times t. And what else? And that's all. This is our first signal. For second signal, or we can specify that the whole duration equals to 1 over capital T. Let's consider second signal. Y of t equals to y0, capital Y0, times square function, and then we have pi over capital T. Use the same hint as we did before. Just rewrite this signal as capital Y0 times 2 capital T. No, let me write it in terms of f. I will name first replacement as f1 in the expression above. f1. And now I introduce a variable f2, which equals to 1 over 2t. And I can rewrite our signal. I can rewrite it as y0 times f2, no, 1 over f2, times f2 times c square function pi times, or I should write actually pi f2 times t. Now it's very easy to find Fourier transform for such signal, for such form of our signal. After Fourier transform, we will get the following, that our signal in frequency domain, y of f, equals, and then we just write what we have. We have y, capital Y0 times 1 over f2 times, and what is the Fourier transform for this part? Capital F2 times c square function and times pi f2 times t.
It will be a triangular waveform.
Triangular, correct, that we have triangular, and then we write that it's triangular of what? Of f divided by f2. And we can replace back. Instead of f2, we substitute 1 over 2t, and we get our signal close to y0 times t times triangular function f times 2t. This is how our signal looks like.
Hello.
Yes, there is just one just
Sir,
thing.
one doubt in x of f, spectrum of x of t.
Sorry?
Sir, there is one doubt in x of f.
X of f. Okay, yes. What's the
Yes,
question?
sir. Sir, the doubt is whenever we find the Fourier transform of any rectangular, means we have got a Fourier transform in terms of rectangular pulse. Okay, so So it's a magnitude which you have find is x naught of t. It should be equal to the area of the rectangle, but it is not matching. Means you have written x of f is equal to x naught of t into rect f into capital T. Okay,
Yes.
but the area that you are getting from the diagram is x of t into 1 upon t, which is x naught. So it is not valid. It is wrong.
No, I think it's fine because you can rewrite it as rectangular f divided by 1 over t. Have in denominator you have 1 over t, and then you have
Okay.
t times 1 over t, and it will be 1, and what you have left is x0.
Uh, okay. So
Yes, and this is what we get exactly here, because you have to place capital T in other form.
okay,
That's
okay, fine, fine.
second option.
Yeah, it's fine. Okay.
Yeah, but it's all these both expressions the same. Same. But yeah, anyway, better to clarify all these doubts. Okay, I just wonder because somehow in my notes and yeah, we should check maybe there was update. But yeah, we should get this result, and now we can go further. So next part, we go to part B. Now we do the following, that we assume that signal x of t and y of t to be mixed into intermediate frequency range first, and we have this expression how we do this. And the whole idea for this discussion is the following, that you have transmitter and you use so-called heterodyne architecture of your transmitter. And then, of course, the same architecture, similar architecture for receiver. How you do this? You divide all these conversion steps into two parts. Generally speaking, you have, for first part, you have digital processing, and for second part, you have analog processing. And usually, you have only one fixed carrier frequency in transmitter or receiver. But then the question, but how can you tune to different channels if you have only one carrier frequency? You have only one oscillator for carrier frequency, but you have in different systems, because you can imagine that you have multiple different channels. Even if you just consider FM broadcasting, yeah, you have different stations. But usually inside receiver or transmitter, you have only one oscillator that generates reference carrier frequency, but somehow you're able to tune between different channels. What you would do possible. But I mean, you have only one carrier frequency. Carrier frequency is only one. Yes, of course, you can use mixer, but after this down conversion or up conversion, because carrier frequency is fixed, what you should do to get the different channels? Idea is very simple. Yes, carrier frequency is fixed and only one, but you select channels based on digital processing. You use digital oscillators, numerical oscillators, numerical control. Yeah, anyway, you use simply digital processing to select the channel that you need. And what you do, you perform additional conversion steps, but in a digital domain. And this is what actually we're going to show you, that we have so-called intermediate frequency, and we perform this transformation. Now we're talking about transmitter side. We perform this transformation in digital domain. So we select any intermediate frequency you want to get, and then we upconvert our signal to this intermediate frequency. And then at second step, we add carrier frequency by multiplying of cosine. I think it's correct. It should be delta f. Okay. But anyway, usually we assume that at second stage, you have this fixed carrier frequency, and it's done by just value of frequency for your carrier oscillator, carrier frequency oscillator. And then by changing this intermediate frequency in digital domain, you can decide at which position in frequency range you place your signal. This is the idea, that using fixed carrier frequency oscillator and additional signal processing, you can decide which frequency you transmit your signal. So I hope it's clear. But if it's not, please ask questions. It's like that it's something. It is, exactly. It's quadrature modulation. Just, no, it's exactly quadrature modulation. It's just some explanation why we need it. And in addition, we say that we have this quadrature modulation. For this quadrature modulation, you have two steps. You have one step at digital domain, and second step, same in analog domain. Okay. No, I mean, there is nothing to repeat. Idea was just that we perform this first shift to intermediate frequency in digital domain. That's all, that we just have fixed carrier frequency oscillator, but we can change, we can choose by ourselves intermediate frequency, performing this shift in digital domain. Just multiply numbers and use signal processing to get different, to get signal at different intermediate frequencies. This is just short discussion. Okay, let's continue. Okay, let's go to next part. I hope we have time to cover part B. We need to draw signal at intermediate frequency. Okay, and first we can just write it. And probably we stop at this point. So part B, we have signal x intermediate frequency of t, and then we get it as x of t times square root of 2 times cosine phi f frequency times t minus phi of t times square root of 2 sine, and then f phi f frequency. So, and we know that the intermediate frequency specified anything 1 over t. What else we know? And that's all. Yeah, we know that what the value of intermediate frequency. And now we need to plot this in frequency domain. How can we do this? All the same, what we did before. We just, first of all, we calculate spectrum by changing cosine to sum of two delta pulses and changing sine to difference between delta pulses. And then what we get? We have x, instead of x of t, we will get x of f, which convolved with signal, with the following signal, square root of 2. By the way, looking at this expression in part B, which component is quadrature and which component is sine phase?
In phase is cosine, quadrature is
We have
sine.
xt, sine phase. We don't take into account cosine and square root of 2. And y of t is quadrature. And also we don't take into account square root of 2 and sine. So sometimes you can find this question like what explicitly, which part is. Okay, so now we have to, of cosine, we have delta pulse, 1/2, 1 over 2 delta pulse, f minus f frequency, plus 1 over 2 delta pulse f plus intermediate frequency. We have 4 cosine minus, then we write second part, y of f, convolution, root of 2, open parenthesis, and then we write the following, 1 over 2j, delta pulse f minus f intermediate frequency, minus 1 over 2j, delta pulse f plus intermediate frequency. So we have following spectrum, and we know how spectrum x of f and y of f like, and now we just need to place them in different positions in our spectrum. Now is the most difficult part. We need to take into account all information that we have about this spectrum. And I think after this, we can just stop our discussion. Okay, I think we consider separately part for x of f and for y of f. How can we write it? We can just write the real part of if, and then it will be imaginary part of if of f part, because it's very easy to distinguish them, yeah, because at first two components we have real numbers, and for second two remaining components you have imaginary numbers. And what we have x of f is what? X of f is rectangular pulse, rectangular shape function. Is my so, and we have two delta pulses. Where should we place them? If we assume that 1 over t, let's say 8 cells. I shouldn't actually make it so large. As this is 1 over t, let's say. So intermediate frequency will be equal to 1 over t. So this is our intermediate frequency. And now we need to place at this intermediate frequency our delta pulse. And we get that we have one rectangular pulse. Here, another rectangular pulse at negative range. There, this is our rectangular pulse. Or maybe I change scaling, because otherwise it's shallow. Yeah, we should. And then we say we have this is our rectangle. This is 1 over t. This is, okay, I will just specify that the range equals to 1 over t. 1 over t. And then we have negative frequencies, minus 1 over t. And we place another rectangular shape function. Minus 1 over t. Now we need to analyze what will be the amplitude. Original amplitude was x0 times t, x0 times capital T, but then we also have to multiply by square root of 2 and divide by 2. This is the resulting amplitude. And just let's plot second part. It's imaginary part of if of f. And let's say we have the same intermediate. See? Of course, we have the same 1 over capital T. and we have minus 1 over capital T, but we have different signal. Our signal we didn't plot it. We didn't plot it, but it will be triangular function. And T. Have y direction. Wider like this. Ah, no. Of course it will be 1 over 2. Oh. For positive, and then for negative, we have minus. Delta pulse with minus. Our triangular function, and have to think about amplitudes. I0 times 2 capital T times square root of 2 and divide by divide by 2, and because I wrote it as imaginary part, actually I have to write minus here. I have to write minus here. I have to place for second part. I have to write this plus. Probably. Plus, because when you move imaginary number up in numerator, you will get minus sign. Then you have y0 times 2 capital T times square root of 2 divided by 2. So this is our check if I forget it. No, this is our two spectrums. Yeah, we have real part and we have imaginary part. And next time we're going to discuss what happens when we go to bandpass range, and then we also consider what steps we need to perform get back our signal from bandpass range, low pass range, but in terms of receiver design. Okay, that's all for today. Thank you for your attention. If there are any questions, I stay here for a couple of minutes. If not, then I want to thank you for attention and wish you productive rest of the week. Thank you and see you next week. Okay, yeah, any questions?